So based on what we just discussed, let's try to solve this example problem about the ideal Brayton cycle analysis and see how we can calculate the net amount of work and the thermal efficiency and so on. Okay, before I go further, let me just try to change my mistake. So now it's not example 22-1, that is example 28. So let's try to read this statement and then try to think about how we can calculate, something that we have to consider for the ideal Brayton cycle analysis. Please give a pause and then read this statement carefully. Okay, now we have a gas turbine power plant, and that is operating on an ideal Brayton cycle. And this Brayton cycle has a pressure ratio of 8. And now we also know the inlet air temperature and pressure at 300 Kelvin and 0.1 megapascal. And we also know the gas temperature or air temperature at the turbine inlet at 1300 Kelvin. And now we are going to use the cold air standard assumption, so which is basically the same as constant specific heats at room temperature. So we basically assume that your air is an ideal gas and its specific heats are constant at room temperature. So that is what the cold air standard assumptions mean. Okay. With that being said, we want to calculate first gas temperature or air temperature at the exit of the compressor and at the exit of the turbine. Okay. And we want to also calculate the back work ratio. I'm going to talk about what this back work ratio means in the later part. And also we will calculate the thermal efficiency. All right. So now what we know and what you're given from the problem statement is the pressure ratio. Okay. So now the pressure ratio, which is defined as P2 over P1. So higher pressure to the lower pressure. And this ratio is given at 8. And also we know that T1 and P1 as state 1. And from these two given conditions, what you can see is we know P2, which is P1 times the pressure ratio, and that gives us 0.8 megapascal. And the maximum temperature, which is T3, that is given as 1300 Kelvin. So now again, can you draw the TS diagram about this ideal Brayton cycle? And as you see from the right hand side, that is how we can draw the TS diagram. It starts from 300 Kelvin, and now we have increased the pressure to 0.8 megapascal with a pressure ratio of 8. Then as a result, the temperature should also go up. Then we have going through this constant pressure heat addition process to reach its temperature at 1300 Kelvin, which is at 0.3. And we have expansion and heat rejection process. So there are a couple of assumptions that we already are given or we also can think of. The first assumption is your working fluid. Now, your working fluid should be in air, and this air is assumed to be an ideal gas with constant specific heats. Okay? So either you are given those values of CV or CP or R and K, or you can find those values from the table. But now you have CV and CP, and from that CV and CP you also can calculate R and K specific heat ratio or vice versa. Now, as I said earlier, the whole gas turbine analysis or ideal Brayton cycle analysis should be based on the open system analysis because air should keep flowing in and out of each component. So that is another very important thing that you have to know. And because we are very interested in kind of regular running of your gas turbine, we assume that is in steady state. And another assumption that we can make is that potential energy and kinetic energy of the air can be ignored. So with those assumptions and given conditions, let's try to solve the first question. What is temperature at the end of a compression process and at the end of the expansion process at the turbine? In other words, can we calculate T2 and T4? So now, in order to calculate T2 first, we have to think about what really happens during the compression process. And again, this compression process in ideal condition should be a reversible adiabatic compression process, or it should be isentropic. Okay. Now, as soon as you see the isentropic process of an ideal gas with a constant specific heat, I really hope that you should be able to come up with certain equations that you can make use of. Okay, so let me write it again. So now, if your working fluid is an ideal gas, okay, with constant specific heat, and now, if this ideal gas goes through the isentropic process, then we can write that equation that describes this process as this. So that is, again, you have to remember that this equation is a result of applying the second law of thermodynamics for an ideal gas with constant specific heat. Okay, so as soon as you use that equation, that means that you already are using the second law of thermodynamics. That's why you don't see the second law of thermodynamics as its full equation set in this solution anymore, because that is the result of applying the second law of thermodynamics equation. Or we can write the same equation in terms of temperature and specific volume as this. Or we also can express the same relation in terms of temperature and pressure as this equation. So which equation should you use? It doesn't really matter, depending on which equation gives you more easy access of solving what you want to calculate. Now, in the case we want to calculate the temperature, but another thing that we know about this problem is that we also know how pressure changes. Then, for that specific example problems, I would use this equation. Okay, so then this equation can be rewritten in terms of the relation between the temperature and pressure at point 1 and 2. That is what we have here. Okay. So from this equation, now T2 can be calculated by temperature at 1 that is given and pressure ratio between point 1 and 2. And we already know what this value means. That is pressure ratio, RP. So by knowing the pressure ratio and the temperature at state 1, we can calculate the temperature at 2, which is given as 443.4 Kelvin. Okay. Then how about the temperature at 4 after expansion process? Again, we should use the same equation, but instead of using index 1 and 2, we use index 4 and 3. Okay. But now, we know T3 because that is given as 1300 Kelvin, but do we know P4 over P3? What do you think? Okay, in order to answer that question, let's go up again to see the TS diagram. Now, if you see 2 and 3, basically we kind of thought that it should be constant pressure heat addition process, and also between 4 and 1, we also have constant pressure process. So what it means is that your P4 should be the same as P1, and your P3 should be same as P2. We have P1 over P2, which is identical with the inverse of the pressure ratio. And now, with this relation, that we also can calculate T4, which is not this number, but 717.7 Kelvin. So with those equations and with those solutions, we now know that all temperatures at all processes. So we know the temperature at 1, 2, 3, and 4. And why those temperatures really matter? Then we have to really think about one more step further. So let's try to calculate the back work ratio. We haven't learned about this back work ratio, but I already discussed and explained how compressor is run, connected with the turbine. Okay? So the combusted gas at high temperature and high pressure, runs the turbine. Okay? And this turbine is connected with the compressor with the same shaft. So what it means is that the power generated by the turbine should run the compressor. Then the remaining portion after we run the compressor should be used as net amount of work that is produced by entire gas turbine system. So the back work ratio actually tells us how much fraction of the turbine work that we can produce is used by the compressor. Okay? So if we have higher back work ratio, that means that we need more power to run the compressor. So exactly same way, then that means that the less amount of work can be actually used for the power generation. Okay? So that is what back work ratio means. So it can be written as this equation. So we use the subscript BW, back and work, and RBW from now on, it means that is a back work ratio. And this back work ratio is defined as the amount of compressor work to the amount of turbine work. And now I'm going to use the symbol WC, okay, instead of WCOM. Now I want to use WT instead of WTURB. Okay. Then in order to calculate the back work ratio, we have to calculate the compression work and turbine work. Then how can you calculate the compression work? Now we should go back to the compressor. Okay. So in order to calculate the work, now you have to instantaneously come up with the first law of thermodynamics. But your compressor in a turbine, in a gas turbine system, should be an open system. Your air should keep flowing in and flowing out. Now let me write up the general equation of the first law of thermodynamics for an open system.
Okay.
Now, how can you write the first law of thermodynamics in general about the open system?
Okay, so that the changing rate of your internal energy, the total internal energy in the control volume, okay, here the control volume should be a compressor, should equal to the net amount of heat input rate and work output rate or power out rate plus m dot I hi plus pei plus kei minus m e dot and he plus pee kei, right?
Then let's remove the unnecessary terms. Okay, we can remove this term because that is steady state, right? And we don't have to worry about this Q because that is adiabatic. And for the W dot, because your compressor needs a work or power, we can write up as W dot C. Okay? So the reason I put a negative sign on in front of WC dot is because we need power input to the compressor. Because we are talking about steady state, that can be written as m dot, same as here is m dot, and we don't worry about potential energy and kinetic energy. And the inlet condition, we already used the index 1, so that should be H1, and HE should be H2. Now, what we know is 0 now it should equal to W dot C plus m dot H1 minus H2, or WC, the amount of power that is needed by the compressor, can be written as m dot H2 minus H1, and from the cold air standard assumption, m dot Cp T2 minus T1 should be your compression power. Okay, so in that case it should be kilowatt. Or I can also write up the same equation in terms of the compression work per unit mass. That is can be calculated by dividing the above equation with m dot. Okay, that is Cp Okay, let me write it down in full. So that is H2 minus H1, the enthalpy change that can be written as Cp times T2 minus T1. That is kilojoule per kilogram. And by applying all numbers that we already have, that gives us 244.6 kilojoule per kilogram. And now we can do the exactly same thing to calculate the expansion work in the turbine. Okay, so now by applying the first law of thermodynamics, I'm not going to repeat the whole entire equation again, but now we have steady state and we don't have any heat input or output because there's adiabatic condition. And now we have minus, we have work or power out by the turbine, and we have M dot and H. Now we have inlet is 3 and exit is 4. So from this equation, the turbine power that is produced by turbine can be written as M dot H3 minus H4 or M dot Cp T3 minus T4. And also we can calculate the turbine work per unit mass as the same thing, turbine power divided by mass flow rate, which is H3 minus H4 or Cp T3 minus T4. And by using all values that we have, that is 585.2 kilojoule per kilogram. Okay. Now, how can you calculate then the back work ratio? So, the back work ratio RBW, which is WC over WT, that is given as 0.418 or 41.8%. Okay. So what it means is that for that specific gas turbine, from the entire power that is generated by the turbine, around 42% is being used to run the compressor, and only 58% is being used to generate power from the entire gas turbine system. So that is what it means. Right? Then how about the thermal efficiency? So thermal efficiency is defined as W net divided by Q in. So how can you calculate the net amount of work? So the net amount of work can be written as Q. Okay, so in that case we already know the turbine work and the compressor work. So now WT minus WC, okay, which is given as 340.6 kilojoule per kilogram. Okay. Now, how can you calculate Q in? So in order to calculate Q in, we have to think about the addition process. Now, by using the first law of thermodynamics for an open system, okay, for steady state, then I can write that equation as this. So steady state makes the left-hand side 0, and we have Q dot in, that is the heat input rate, and minus W dot, but we don't have the power generated or needed by during this constant pressure heat addition process, and we have M dot, and we have inlet H2 minus outlet H3. Okay, so Q in dot can be expressed in terms of M dot H3 minus H2 or M dot Cp T3 minus T2. Or we can write up the Q in per unit mass as H3 minus H2, which is Cp T3 minus T2, and the value of this Q in is 760.4 kilojoule per kilogram. So from those values, then the thermal efficiency of that gas turbine is 0.448 or 44.8%.